Hello there, and welcome to Smart Student TV, the only channel where academic and professional prowess is nurtured right from the comfort of your living room. Whether you are a student striving for excellence, a professional looking to sharpen your skills, or simply a lifelong learner, you are in the right place. In today's tutorial, we dive into another very exciting and crucial topic: photographic technology. A camera is one of the most valuable scientific tools ever invented. Its application spans multiple fields, from medicine to astronomy, from criminal investigations to environmental science. Cameras are not just tools for capturing moments. They are windows into worlds beyond human perception. When attached to advanced optical instruments such as microscopes in biology or telescopes in astronomy, cameras can reveal intricate details invisible to the naked eye. For example, a camera attached to a microscope can magnify and capture details of a cell structure, aiding biologists in groundbreaking discoveries. In scientific research, specialized photography is indispensable. The images captured are reproducible in academic journals, magazines, and textbooks, enabling scientists to share findings with pinpoint accuracy. Remote control cameras can venture into hazardous zones, such as nuclear explosion sites, or into confined spaces like the human throat or stomach, delivering vital information without endangering human lives. Photographic evidence is universally accepted as accurate and truthful, making it a cornerstone of forensic investigations. No medical, industrial, or scientific research center would be considered complete without a fully equipped photographic facility. Objectives of this tutorial. By the end of this tutorial, you will 1. Understand the fundamental principles of photography. 2. Identify the different parts of a camera and their functions. 3. Learn about various types of cameras and their mechanisms. 4. Explore film processing techniques, including black and white and color photography. 5. Understand the applications of digital, video, and projector photography. 6. Appreciate the importance of mastering photography skills in laboratory science. A brief historical perspective on photography. Photography has a long and interesting history. It started in the early 19th century when people discovered that certain materials change when exposed to light. These discoveries made it possible to capture and keep images for a long time. At first, the process was slow, and taking one photograph could take hours. But over time, better techniques were developed, making the process faster and the images clearer. The invention of flexible film made cameras easier to carry and use, allowing more people to own and operate them. Later, color photography was introduced, adding vibrancy and realism to pictures. This changed how we documented events and discoveries, both in everyday life and in science. With further improvements, instant cameras were created, allowing people to see their photos right after taking them. The shift from film cameras to digital cameras was another big milestone. Digital cameras made it possible to store hundreds of photos on a small memory card and view them instantly on a screen. In science, photography became an important tool. Scientists started using cameras to study very small objects under microscopes and very distant objects using telescopes. High-speed cameras made it possible to capture events that happened too fast for the human eye to see, like a water droplet hitting a surface. Today, photography is everywhere. From medical imaging technologies like MRI and CT scans to drones capturing images from the sky, photography helps scientists and researchers observe, analyze, and share information like never before. It has become an essential tool in almost every field of science and technology. Benefits of photographic technology. Photography isn't just about clicking a button and capturing a nice picture. It's about precision, observation, and storytelling. In science, photos play a crucial role in documenting findings, identifying patterns, and communicating results effectively. Imagine a doctor examining an X-ray image. Without photographic technology, diagnosing a broken bone or spotting a tumor would be nearly impossible. Similarly, in environmental studies, aerial photography from drones can capture large forest areas, helping scientists monitor deforestation and plan conservation strategies. Photography also allows remote data collection. For example, cameras on satellites monitor weather patterns and climate changes from space. These images are then analyzed to predict hurricanes, track wildfires, and measure ice cap melting. In short, Photography makes it possible to see, document, and share scientific discoveries accurately and efficiently. Photography has countless applications in science, lab work, and academics. Let's break it down with a few examples. 1. Medicine. Think of medical imaging, X-rays, MRIs, and CT scans. These technologies rely on photographic techniques to give doctors a clear view of what's happening inside the body. 2. Biology. Microscopic photography allows scientists to study cells, bacteria, and viruses in detail. For example, researchers studying the COVID-19 virus used high-resolution imaging to understand its structure. 3. Astronomy. Telescopes equipped with cameras have captured stunning images of distant galaxies, planets, and stars. These photos provide insights into space phenomena that are impossible to observe with the naked eye. 4. Forensics. Crime scene investigators rely on photography to document evidence. A single photograph can capture details like fingerprints, bloodstains, or footprints, which can be crucial in solving a case. 5. Academics. In education, photography is used in teaching and learning materials. Textbooks and academic journals rely heavily on high-quality photographs to explain concepts clearly. Teachers use photographic slides and digital images during presentations to enhance understanding. 6. Publishing. Scientific and educational books require accurate and high-resolution images to illustrate processes, experiments, and findings. 7. Research documentation. Researchers use photography to record experimental results step by step, ensuring their findings are well documented and reproducible. Without photography, many scientific and academic breakthroughs would have remained hidden or impossible to verify. If you're working in a lab, you might wonder, do I really need to know photography? The answer is, absolutely yes. Here's why. 1. Accurate documentation. Imagine running a complex chemical experiment and needing to show your results clearly. A well-taken photograph can capture every detail, colors, textures, and patterns that might be missed in a written description. 2. Effective communication. Photos make it easier to share findings with colleagues, supervisors, or in presentations. A single image can communicate more information than paragraphs of text. 3. Enhanced credibility. Clear, high-quality photographs add professionalism to your reports and research papers. They also make your work easier to verify and replicate. So, whether you're capturing microscope slides, recording experimental results, or documenting fieldwork, photography is a skill every lab technologist should have. In conclusion, photographic technology is more than just capturing images. It is about seeing, sharing, and understanding the world in ways previously unimaginable. Photography is an art, a science, and a form of technology that has revolutionized the way humans document and interpret the world. But how does this incredible technology actually work? Let's dive into the principles of photography, explore the camera, its parts, types, and the lenses that make magic happen. The principle of photography. At its core, photography is the process of capturing light to create an image. The word itself comes from the Greek words photos, light, and grapho, to draw. Essentially, a photograph is a drawing made with light. The fundamental principle of photography revolves around the interaction between light and a photosensitive surface, such as film or a digital sensor. Light enters a camera through an opening called the aperture, passes through a lens, and gets recorded on a light-sensitive surface, either film in older cameras or a digital sensor in modern ones. The result: a photograph. To break it down further. 1. Light source. This could be natural light from the sun or artificial light from a bulb. 2. Subject. The object or scene you're photographing. 3. Camera lens. Focuses and directs the light onto the recording surface. 4. Sensor or film. Captures and processes the light to create an image. Without light, photography simply isn't possible. This is why photographers often talk about good lighting and spend time adjusting light sources or camera settings. The camera. The camera is essentially a light-proof box equipped with a lens, a shutter mechanism, and a recording surface, either film or a digital sensor. Whether you're using a smartphone camera, a professional DSLR, or an old film camera, They all share the same basic structure. Parts of a camera. Let's break down the main parts of a modern digital camera. 1. Lens. The lens is arguably the most important part of the camera. It collects light and focuses it onto the sensor. Example: a wide-angle lens is perfect for capturing landscapes, while a telephoto lens is used for wildlife photography. 2. Shutter. The shutter is like a curtain that opens and closes to let light hit the sensor. The shutter controls the length of time light is allowed to hit the sensor. The duration the shutter stays open is called the shutter speed, which controls motion blur and exposure. A fast shutter speed freezes motion, e.g., a bird in flight, while a slow shutter speed captures motion blur, e.g., flowing water. 3. Aperture. Located in the lens, the aperture is like the pupil of an eye. It controls the size of the opening that allows light to pass through the lens. A wider aperture lets in more light, which is useful in low light conditions. 4. Viewfinder or screen. A viewfinder is the part of a camera that allows the photographer to see what the camera's lens is capturing. It's an eyepiece that you hold close to your eye to compose and frame your photo. 5. Sensor. In digital cameras, the sensor captures light and converts it into digital signals. 6. Memory card. Stores the captured images. 7. Battery. It powers the camera. Next, let's look at the types of cameras. Cameras come in different shapes and sizes, each serving specific purposes. Let's look at the most common types explained in simple terms. 1. The simple camera. This is the most basic type of camera. It usually has a fixed lens and few controls. You just point and click. Best for beginners and casual photography. 2. The single lens reflex, SLR, camera. This camera uses a system of mirrors to let you see exactly what the lens sees. When you press the shutter button, the mirror flips, and the image is captured. The Nikon F-series cameras are good examples of this cameras. They are best for professional photographers who need precision and control. 3. Rangefinder camera. Rangefinder cameras use a special focusing system where two images are aligned to focus on the subject. They are compact and produce sharp images. The Leica M-series camera is a good example of this types of cameras. They are best for street photography and travel. 4. Twin lens reflex, TLR, camera. These cameras have two lenses, one for viewing and one for capturing the image. You usually look down into the camera to frame your shot. Rolleiflex camera is an example for this camera type. They are best for portrait and studio photography. 5. DSLR, digital single lens reflex. This is a digital version of the SLR camera, but instead of film, it uses a digital sensor to capture images. The Canon EOS 5D Mark IV are good examples for this camera type. They are best for versatile photography, from landscapes to portraits. 6. Mirrorless cameras. These cameras don't have a mirror system, making them smaller and lighter than DSLRs. Example: for this camera type are Sony Alpha A7 III. They are best for travel and everyday photography. 7. Point-and-shoot cameras. They are small, lightweight, and easy to use. You just point the camera and click. Examples are Canon PowerShot series. They are best for casual and travel photography. 8. Smartphone cameras. Built into smartphones, these cameras are now incredibly advanced and capable of high-quality images. Camera lenses. Lenses are critical components of a camera, as they determine how light is captured and directed onto the sensor. Different lenses serve different purposes, and choosing the right lens can dramatically impact the final image. 1. Prime lenses. They have a fixed focal length, and are known for sharpness and clarity. They are great for portraits and low-light photography. 2. Zoom lenses. They offer adjustable focal lengths. They are versatile and great for situations where you can't physically move closer to the subject. 3. Wide-angle lenses. They capture a broad field of view. They are ideal for landscapes and architectural photography. 4. Telephoto lenses. These lenses bring distant subjects closer. They are perfect for wildlife and sports photography. 5. Macro lenses. They are designed for extreme close-ups. They are used for photographing small subjects like insects or flowers. 6. Fisheye lenses. They offer an ultra-wide view with a curved, distorted effect. They are often used for creative shots. Next, let's get to understand camera focus and the contribution of camera lenses in bringing about focus. In photography, focus refers to the sharpness and clarity of an image, achieved by adjusting the camera lens to ensure that light converges accurately on the camera sensor or film. Proper focus ensures that the subject appears crisp and detailed, while out-of-focus areas become blurred. Focus can be manual, adjusted by the photographer, or automatic, handled by the camera's autofocus system. Camera lenses play a critical role in achieving focus, as they control how light rays are directed onto the image sensor. Different lenses, wide-angle, telephoto, macro, and prime, offer varying focal lengths and depth of field control, enabling photographers to isolate subjects, create background blur, bokeh, or capture expansive landscapes with clarity. High-quality lenses minimize distortions and aberrations, ensuring precise focus even in challenging lighting conditions. In essence, lenses act as the photographer's eye, dictating how light is captured and interpreted, making them essential tools for achieving accurate focus and artistic expression in photography. The camera controls. Next, let's dive deeper into camera controls. Whether you're using a professional DSLR, a mirrorless camera, or even your smartphone, the basic controls that determine how your photos turn out are pretty much the same. We're going to focus on 3 major things: shutter speed, aperture, and film or sensor in digital cameras. Think of these as the building blocks of photography. 1. Shutter speed. The blink of your camera. Imagine your camera as an eye. The shutter acts like your eyelid, opening and closing to let light in. The time your eye, or shutter, stays open is called shutter speed. Depending with speed, shutters can be categorized into 1. Fast shutter speed. Think of blinking quickly. A fast shutter speed, like 1/1000th of a second, freezes fast action. For example, if you're taking a photo of a bird in mid-flight or someone jumping in the air, a fast shutter speed will capture the moment without any motion blur. 2. Slow shutter speed. Now imagine keeping your eye open for a few seconds. A slow shutter speed, like 1/10th of a second or even a few seconds, allows more light to hit the sensor. This is great for nighttime shots or creative effects like light trails from car headlights. But if the camera or subject moves, you'll get motion blur. A good example of this would be photographing a waterfall. With a fast shutter speed, every droplet of water is frozen in mid-air. But with a slow shutter speed, the water appears silky and smooth, flowing like a soft ribbon. Both results are beautiful, but they tell different stories. 2. Aperture. Next, we have the aperture. If the shutter is like your eyelid, the aperture is like the pupil of your eye. It controls how much light enters the camera. Depending with the aperture size, apertures can be classified as 1. Wide aperture, low f number like f/1.8. The pupil is wide open, letting in a lot of light. This is perfect for low light situations and creates a blurry background, shallow depth of field. Photographers use this for portraits where they want the subject in sharp focus but the background beautifully blurred. 2. Narrow aperture, high f number like f/16. The pupil is very small, letting in less light. This is used for landscape photography where you want everything in focus, from the flowers in the foreground to the mountains in the background. Imagine you're taking a picture of a friend in a park. With a wide aperture, f/1.8, your friend will be sharp and in focus, while the background becomes a soft, dreamy blur. On the other hand, if you're capturing a wide scenic view of mountains, you'll want a narrow aperture, f/16, to make sure everything is sharp and clear. Now, here's where things start to come together. Shutter speed and aperture work hand in hand. If you open the aperture wide, f/1.8, you might need a faster shutter speed to prevent too much light from overexposing the photo. Similarly, if your aperture is very narrow, f/16, you may need a slower shutter speed to let enough light in. 3. Film. Before digital cameras, film was the heart of photography. Today, digital cameras use a sensor instead, but they both serve the same purpose: to record light. Camera film is a light-sensitive material that captures images when exposed to light. It is a strip or sheet of transparent film base coated on one side with a gelatin emulsion containing microscopically small light-sensitive silver halide crystals, usually silver bromide. It's made of several layers, including 1. Base, the thickest layer that supports the other layers. Originally made of glass, today's bases can be made from a variety of materials, including paper, aluminum, or plastic. 2. Emulsion, a gelatin-based layer containing silver halide crystals that react to light. The size and other characteristics of these crystals determine the film's sensitivity, contrast, and resolution. 3. Anti-halation backing, a layer that helps reduce halation. Halation is a photographic effect that occurs when light reflects off a film's emulsion, creating a soft glow around bright areas of an image. It's often described as a halo or soft halo effect. 4. Protective coating, a layer that protects the film. The combination and order of these layers varies depending on the type of film, such as color, black and white, slide, or instant. When exposed to light, the film creates an invisible image called a latent image. To make the image visible, the film is treated with chemicals in a process called developing. How film works. When light enters the camera and hits the film, this light-sensitive material, causing a chemical reaction to happen. This reaction records the image. The sensitivity of the film to light is measured in ISO. Low ISO, e.g., ISO 100, is less sensitive to light but produces high-quality, noise-free images. Great for bright, sunny days. High ISO, e.g., ISO 1600, is more sensitive to light but adds grain or digital noise to the image. Used in low-light situations. When light hits photographic film, a chemical reaction occurs between the light and the silver halide crystals in the film. The silver halide crystals react with the light, creating silver ions. The amount of light that hits the film determines the extent of the reaction. Following this light exposure, different parts of the film shall be exposed to different amounts of light. It will change more where the image have been exposed to more brighter light and less where it have been exposed to a dim light. This will create a latent image which may not be permanent or visible. These is because the halide salts are able to pick light which is just brief enough to initiate the darkening process of the image. At these stages, the image is not visible to the eye. The silver-coated film is kept in total darkness and shall require to be treated with a chemical solution, which develops and accelerates the chemical change until when a strong visible black-silver image appears. These images, however, not permanent, and it have to be further fixed using another chemical which makes the remaining silver salts to be sensitive to any further exposure to light. These remaining silver salt can now be washed away, and a stable negative image is left behind which can safely be left exposed to light without any further changes occurring. Converting the negative image into a positive image is done by shining a beam of light through the negative, usually in a darkroom, into another light-sensitive sheet of photographic paper. This paper is then developed and fixed to give a positive image that can now be enlarged into various desired sizes and many copies made from it in a process called printing. Next, let's delve into the film processing techniques. Film processing is a fascinating journey that transforms the images you've captured on film into tangible photographs. Film processing is the method of developing photographic film to produce a visible image. When you take a picture with a film camera, the film inside the camera records the image as a latent, invisible image. Through chemical treatments, this latent image becomes visible and stable, resulting in a negative or positive image that can be printed or scanned. There are two basic types of film processing: black and white, BNW, and color films, each requiring distinct chemical treatments to develop images from exposed film. Color film processing involves more chemicals and steps compared to black and white. Furthermore, color photography development also requires stringent temperature control. Also, due to the precision required, color film development often benefits from specialized equipment to maintain consistent temperatures and agitation, whereas BNW film can be processed with more basic tools. Generally, black and white film processing is generally less expensive and more accessible for home developers, while color processing can be more costly and may require access to specialized equipment or professional labs. Equipment used in film processing. To develop film, you'll need several key pieces of equipment. 1. Developing tank. A light, tight container where the film is processed. It allows you to pour in chemicals without exposing the film to light. 2. Film reels. These hold the film in place inside the developing tank, ensuring even development. They come in sizes to accommodate different film formats. 3. Measuring cylinders. Used to measure and mix chemicals accurately. 4. Thermometer. Temperature control is crucial in film development, so a thermometer ensures chemicals are at the correct temperature. 5. Timer. Precise timing is essential for each step of the development process. 6. Darkroom or changing bag. A completely dark space where you can load the film onto reels without exposing it to light. A changing bag is a portable option if a darkroom isn't available. Chemicals used in film processing. Developing film involves several chemical solutions. 1. Developer. This chemical converts the latent image on the film into a visible one. Common developers include hydroquinone and phenidone. 2. Stop bath. A weak acid solution that halts the development process immediately, ensuring the film doesn't overdevelop. 3. Fixer. This solution removes any unexposed silver halide crystals, making the image permanent and no longer sensitive to light. The following is the step-by-step procedure to generate the negative. 1. Preparation. Ensure all your equipment is clean and your chemicals are prepared at the correct temperatures. Set up your workspace in a darkroom or use a changing bag to handle the film. 2. Loading the film. In complete darkness, open the film canister and carefully load the film onto the reel. Place the loaded reel into the developing tank and secure the lid. 3. Developing. Pour the developer into the tank, ensuring it fully covers the film. Agitate gently according to the developer's instructions to ensure even development. After the specified time, pour out the developer. 4. Stopping development. Pour the stop bath into the tank to halt the development process. Agitate briefly, then drain the solution. 5. Fixing. Add the fixer to the tank to make the image permanent. Agitate as directed, then pour out the fixer. 6. Washing. Rinse the film thoroughly with water to remove any residual chemicals. Proper washing prevents future degradation of the negatives. 7. Drying. Carefully remove the film from the reel and hang it in a dust-free environment to dry completely. Using a wetting agent can help prevent water spots. Next is the procedure for generating the positive print. 1. Setting up the darkroom. You'll need an enlarger, photographic paper, and trays for chemicals. Ensure the room is light-tight and equipped with a safe light appropriate for the paper you're using. 2. Creating a test strip. To determine the correct exposure time, expose a strip of photographic paper at varying intervals. Develop the strip to see which exposure produces the best result. 3. Exposing the photographic paper. Place the negative in the enlarger and project the image onto the photographic paper. Set the determined exposure time and expose the paper. 4. Developing the print. Place the exposed paper into the developer tray, gently agitating until the image appears. This usually takes about 1 to 2 minutes. 5. Stopping development. Transfer the paper to the stop bath for about 30 seconds to halt development. 6. Fixing the image. Move the paper to the fixer tray for the recommended time, typically 2 to 5 minutes. 7. Final rinse. Immerse the paper in a diluted wetting agent solution to promote even drying and minimize water spots. 8. Drying. Hang the paper in a dust-free environment, using weighted clips to prevent curling. Allow the paper to dry completely before cutting and storing. Finally, let's look at the darkroom. A darkroom is a controlled environment where photographers develop film and create prints from negatives. This space is meticulously designed to exclude all light, preventing exposure of light-sensitive materials during processing. The primary function of a darkroom is to facilitate the development of photographic film and the enlargement of images onto photographic paper, allowing photographers to produce prints that align with their creative vision. Essential features of a darkroom. 1. Dry area. This space is designated for tasks like handling unexposed film, setting up enlargers, and preparing photographic paper. Maintaining a clean, dust-free environment here is crucial to prevent contamination of light-sensitive materials. 2. Wet area. Equipped with sinks and trays, this section is used for chemical processing, including developing, stopping, fixing, and washing prints. Proper ventilation is essential to dissipate chemical fumes and ensure a safe working environment. Basic equipment and their functions. A well-equipped darkroom includes several key pieces of equipment. 1. Enlarger. An optical device that projects light through a negative onto photographic paper, allowing the creation of enlarged prints. It enables precise control over focus, exposure time, and image size. 2. Safe light. A specialized light source that emits wavelengths to which photographic paper is less sensitive, typically red or amber. This illumination allows photographers to see while working without exposing the paper prematurely. 3. Developing trays. Containers that hold chemical solutions, developer, stop bath, and fixer, used sequentially to process exposed photographic paper. Each tray is designated for a specific chemical to prevent cross-contamination. 4. Tongs. Tools used to handle photographic paper during processing, minimizing direct contact and reducing the risk of contamination or damage to the prints. 5. Timer. A device to monitor exposure times and chemical processing durations accurately, ensuring consistency and repeatability in print quality. 6. Chemical storage bottles. Containers used to store photographic chemicals safely, protecting them from contamination and prolonging their usability. Safety considerations in a dark room. 1. Always handle chemicals with care. 2. Work in a well-ventilated area to avoid inhaling fumes. 3. Wear protective gloves to prevent skin contact. 4. Store chemicals securely. Finally, let's discuss the digital camera photography and video camera photography. Photography has undergone a remarkable transformation over the years, evolving from traditional film-based methods to the digital and video technologies we utilize today. This comprehensive discussion delves into the essence of digital and video photography, highlighting their distinctions from non-digital photography, advantages, fundamental features, components, operational mechanisms, applications, and future prospects. Digital photography. Digital photography captures images using electronic sensors that convert light into digital data. Unlike film photography, which relies on chemical reactions to record images, digital photography employs sensors such as CCD, charge-coupled device, or CMOS, complementary metal oxide semiconductor, to capture light and convert it into electronic signals. These signals are then processed and stored as digital files, typically in formats like JPEG or RAW. Video photography, on the other hand, involves capturing moving images, creating the illusion of motion through a sequence of frames displayed in rapid succession. Modern video cameras record these frames digitally, allowing for high-definition, HD, and ultra-high-definition, UHD, content. The integration of digital sensors in video cameras has significantly enhanced image quality and editing capabilities. 2. Differences from analog, film, photography. While they both operate in almost similar ways, digital photography comes with a number of features that gives it added functionalities and hence more advantages. This include 1. Image capture and processing. In film photography, images are captured on light-sensitive film, which undergoes chemical development to produce photographs. This process is time-consuming and requires specialized equipment. In contrast, digital photography captures images electronically, enabling immediate review and editing. This immediacy is a significant advantage for photographers seeking efficiency and flexibility. 2. Cost and convenience. Digital photography eliminates the need for film rolls and chemical processing, reducing ongoing costs. Additionally, digital images can be stored, edited, and shared electronically, streamlining workflows and enhancing convenience. This ease of dissemination has transformed how photographs are shared and consumed globally. 3. Advantages of digital and video photography. 1. Immediate feedback and editing. Digital cameras provide instant feedback, allowing photographers to review images immediately and make necessary adjustments. This feature is particularly beneficial in dynamic shooting environments where quick decision-making is crucial. 2. High storage capacity and flexibility. Digital media offers substantial storage capacity, enabling photographers to capture thousands of images without the need to change film rolls. This flexibility is advantageous for events or projects requiring extensive shooting. 3. Advanced features and integration. Modern digital cameras come equipped with features such as autofocus, image stabilization, and connectivity options like Wi-Fi and Bluetooth. These advancements enhance user experience and integrate seamlessly with other digital tools and platforms. 4. Basic features, parts, and functions. Digital cameras. 1. Sensor. The heart of a digital camera, the sensor captures light and converts it into digital data. 2. Lens. Focuses light onto the sensor, determining the field of view and depth of field. 3. Processor. Processes the data from the sensor, converting it into a viewable image. 4. Display screen. Allows for image review and menu navigation. 5. Storage media. Holds the digital files, such as SD cards. Video cameras. 1. Sensor. Captures moving images, converting them into digital signals. 2. Lens. Adjusts focus and zoom to frame the scene appropriately. 3. Processor. Compresses and encodes video data for storage or transmission. 4. Microphone. Records audio to accompany the video. 5. Storage media. Stores video files, often on SD cards or internal drives. 5. Mechanism of action. Digital cameras look very much like ordinary film cameras, but they work in a completely different way. When you press the button to take a photograph with a digital camera, an aperture opens at the front of the camera and light streams in through the lens. So far, it's just the same as a film camera. From this point on, however, everything is different. There is no film in a digital camera. Instead, there is a piece of electronic equipment that captures the incoming light rays and turns them into electrical signals. This light detector is one of two types, either a charge-coupled device, CCD, or a CMOS image sensor. If you've ever looked at a television screen close up, you will have noticed that the picture is made up of millions of tiny colored dots or squares called pixels. Laptop LCD computer screens also make up their images using pixels, although they are often much too small to see. In a television or computer screen, electronic equipment switches all these colored pixels on and off very quickly. Light from the screen travels out to your eyes, and your brain is fooled in to see a large, moving picture. In a digital camera, exactly the opposite happens. Light from the thing you are photographing zooms into the camera lens. This incoming picture hits the image sensor chip, which breaks it up into millions of pixels. The sensor measures the color and brightness of each pixel and stores it as a number. A video camera works almost the same way, except that it captures and records moving images and sound. It does this through a combination of optical, electrical, and digital processes. The camera lens focuses light onto an image sensor, which converts the light into an electrical signal. This signal is then processed by the camera's electronics, which convert it into a digital format. The digital information is then stored on a memory card or other storage medium. The camera also records audio through a built-in microphone or an external microphone, which is synchronized with the video footage. The recorded video and audio can be played back on the camera's screen or transferred to a computer or other device for editing or viewing. 6. Applications of digital photography. 1. Professional photography. Widely used in portrait, commercial, and event photography due to its efficiency and image quality. 2. Journalism. Enables quick capture and dissemination of images, essential for news reporting. 3. Personal use. Common in smartphones and consumer cameras, allowing for everyday photography. Application of video photography. 1. Film and television production. Digital video cameras are standard in the industry, offering high-quality footage and ease of editing. 2. Content creation. Utilized by vloggers and online creators for producing engaging content. 3. Surveillance. Employed in security systems for monitoring and recording activities. The future of digital and video photography is promising, with ongoing advancements in sensor technology, image processing, and integration with artificial intelligence. These developments are expected to enhance image quality, automate editing processes, and provide more intuitive user experiences. Additionally, the rise of immersive technologies like virtual and augmented reality presents new opportunities for photographers and videographers to explore innovative storytelling methods. Last but not least, let's finish this tutorial by looking at the projectors. Projectors are optical devices used to project images, videos, or presentations onto a large surface, typically a white screen or wall. They have become indispensable tools in various fields, including science, technology, education, business, and entertainment. By magnifying content and making it visible to large audiences, projectors enhance communication, learning, and collaboration. Uses of projectors. Projectors serve diverse purposes across different sectors. 1. Education. Used in classrooms and lecture halls for teaching and presenting academic content. 2. Science and technology. Vital in laboratories and conferences for demonstrating research findings. 3. Business. Facilitate meetings, presentations, and corporate training. 4. Entertainment. Key components in cinemas and home theaters. 5. Art and design. Aid in creating large-scale art installations and designs. 3. Components of projectors. Every projector consists of several key components. 1. Lens. Focuses and projects light onto the screen. 2. Light source. Provides the illumination needed for projection. 3. Mirror and reflector system. Directs and enhances light. 4. Imaging system. Converts the content into a projected image. 5. Cooling system. Prevents overheating of the internal components. 6. Power supply. Provides electrical energy to operate the projector. 7. Control panel. Allows users to adjust focus, brightness, and image alignment. 4. Types of projectors. A film strip projector. Projects static images from strips of film. Commonly used in educational settings for storytelling and diagram explanations. Advantages. Portable, easy to operate, cost-effective. Disadvantages. They are only limited to still images. B. Overhead projector. OHP. Uses transparent sheets to project written or drawn content. Widely used in classrooms and business meetings. Advantages. They are easy to use, interactive. However, they are bulky, outdated compared to digital projectors. C. LCD, liquid crystal display, projector. They utilize liquid crystal panels to project digital content. They are common in modern educational and professional environments. Advantages. High-resolution images, vibrant colors. However, they are expensive, requires regular maintenance. 5. The film strip in projectors. Film strips are sequences of images printed on transparent film. They are fed through film strip projectors and illuminated by light to display images on a screen. These strips were historically used in classrooms to present educational visuals and are still appreciated for their simplicity. 6. Care and maintenance of projectors. Proper care and maintenance of projectors ensure their longevity and performance. 1. Regular cleaning, dust lenses, filters, and vents. 2. Proper storage. Store in a dry and cool environment. 3. Avoid overheating. Ensure adequate ventilation during use. 4. Handle bulbs carefully. Replace projector bulbs as per manufacturer recommendations. 5. Calibration. Periodically adjust focus and alignment. Projectors remain powerful tools in science, technology, and academics, enhancing communication, teaching, and collaboration. Whether using traditional film strip projectors, overhead projectors, or modern LCD projectors, each type offers unique benefits suited to specific needs. By understanding their components, types, and proper care, users can maximize the value and efficiency of projectors in various applications.